Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to module 4.3. As you may recall, in the last module, I introduced this concept of a spinor. That is, the idea that when you think of an object pointing in some direction, what you are used to is this vector representation of this object, which is in terms of its x, y, and z components. And what I introduced in the last module was this spinor representation, where you write its up component and its down component. And these are not at all intuitive, as I had mentioned. And what I said was, well, if you accept this, what I'll try to do is, based on this, we'll try to get some results that are useful. And then in a subsequent module, possibly the next one, I'll try to come back and justify it a little better. Okay. Now, what we did in the last module then is, using this, I showed that if you were trying to write the connection to the contact, this gamma matrix, then it would have a form like this, where P is this polarization of the magnet, and it's a vector that points in the direction of the magnet. This N is a unit vector in the direction of the magnet. And what enters here is the Z component of that, that's on the diagonal, and the X and Y components enter in the off diagonal. And as I mentioned, if you did not have X and Y, the rest is kind of intuitive. But the X and Y, these off diagonal things, that's what really requires this formal mathematical basis transformation that we did in the last module. Now, here I want to start by explaining a little bit about this electron density inside the channel. You see, if you think about it, this NEGF equations, what I said was, once you have the H's and sigmas, you can calculate the electron density, you can calculate density of states, you can calculate current, and so on. What I want to talk about is, let's say you have calculated this Gn, the one that's like number of electrons. How would I interpret it? Now, let me explain what I mean. See, usually, as you know, if your device has, say, 4 points, then your matrices would all be 4 by 4. And your Gn would have been like 1, 2, 3, 4. And if you go to this point, it tells you electrons, number of electrons at point 1, 2, 3, 4. Okay. But now, because we have introduced spin, at the location 1, you actually have a up spin and a down spin. So, as I said earlier, that formally, when you include spin, all that happens is every matrix gets twice as big. So the same equations, just the matrices are twice as big. And so now when I go to the 1, 1 point, actually what I have here is a 2 by 2 matrix. So if I looked at this quantity Gn at any point, I'd be looking at a 2 by 2 matrix. Okay? And the question is, how do I interpret it? So I've got this Gn at a particular point, looks like a 2 by 2 matrix. There's this up component, down component, up, down, this matrix. So how do I interpret this? Okay. And what I'll be trying to show is that you could interpret it in the following way, and that is, let's move this back a little bit, put a half here. This will be like n plus SZ, n minus SZ, and then Sx minus ISY, and Sx plus ISY. Now, again, what's n? Well, it's the total number of electrons at that point, up, down included. What is Sz? Well, it's a net spin in the z direction. Sx, Sy, again, spins in x and y directions. So you might say, well, but how do I understand this one? And what I'd say is, well, if the x and y were not there, then actually it is fairly straightforward to see. Because you could say, supposing we have a point where, let's say I got 60 up electrons and 40 down electrons. Then the total number of electrons, n, is equal to 100. 60 red types, 40 blue types, total is 100 n. And what is the spin, net spin? Well, this is the type that has a positive spin, and that is the type that has a negative spin. So the net spin is like 60 minus 40. You see, both types have the same charge. So when I look at the total charge, or the total number of electrons is just the addition. When I look at the net spin, it's like the difference. So I get 20. You see? And now, you see, if I write n plus sz, that would be like 100 plus 20, and then I have a half in front, so it would become like 60. Because 100 plus 20 is 120, divided by 2, that's 60. And if I go here, it will be 100, take away 20, that's 80, divided by 2, that's 40. 0, 0. So that's what Gn would look like if I had a situation where, 60 ups and 40 downs. That's what it would look like. And that's a special case of this. And that's what I said, as long as it is all in the z direction, no x and y components, it's straightforward. You can understand it easily. The part that's not so easy to understand is the xy components, you see. And again, one way to do it is, do it like we did last time. Write it this way. If you had spins pointing in some direction, write it this way in a certain basis and transform it. What I'll be doing is trying to show you how this comes about in a slightly different way, starting directly from here. Okay? But the final result that I'm trying to get at is this one, and you'll notice the similarity here. You see? And this will allow this similarity. Because of this similarity, which comes up often, there is a set of matrices that are convenient to define, this Pauli spin matrices, which is what I'll be kind of finishing this module with. We'll get to that in a minute. But let me try to talk a little more about this one, how to see that. Okay. Now, one way would be, see, sometime back when we were doing the NEGF equations, I said, well, what is this Gn like? Well, it is like this psi dagger. That electron has a certain wave function, and you multiply it by its conjugate transpose, and that's what gives you the Gn. And the reason this is convenient is, when you have many electrons, you cannot add their wave functions. That's one point I made, that this is where it's different from coherent sources. That with light, if it is coherent light, like laser light, you can add electric fields. But if it is incoherent, you have to add powers. With electrons, there is nothing quite like the laser light with normal electrons. And what we can add is this psi dagger, these bilinear things. Okay. Now, so let's say we had an electron that was pointing in some direction n. Question is, what is the corresponding Gn for that electron? And the advantage of this is that, well, if you had another electron in some other direction, well, we could add them up one by one. Okay. Now, what is the Gn for something that looks like this? Well, I'd say that psi looks like Cs, and psi dagger, that's the conjugate transpose. So I could write it as, conjugate is C star, and transpose means what used to be a column vector becomes a row, like this. That's it. So when you multiply it out, it will look like CC star, CS star, SC star, SS star. Okay. Now, what's CC star? I guess we could write this down. You're taking this quantity, multiplying it by its complex conjugate. The phase factor goes away, so you just get cosine square half theta. Similarly, when you do SS star, you just get sine square half theta. Actually, let me write it here. That way it will be kind of close. Right here. So you'll have cosine square a half theta and sine square a half theta. Now, I need CS star, which is this times the complex conjugate of this. So you have cosine half theta, sine half theta. But when I take the complex conjugate of this, you see this is minus, this also becomes minus. So when I multiply, they don't cancel. Instead, I get twice. So what you'd have is something like cosine half theta, sine half theta, and then e to the power minus I phi. And here, what you'd have is exactly the same but complex conjugate. Cosine half theta, sine half theta, exponential plus I phi. Okay. Now, we could do a little bit of trigonometry again. This cosine square half theta is actually half of, so let me pull a half out so that I can look at 2 cosine square half theta, and that's actually 1 plus cosine theta. That's it. And this 2 sine square half theta, that's like 1 minus cosine theta. And here I have 2 cosine half theta, sine half theta, that's actually like sine theta. And the e to the power minus I phi. And then here you have sine theta, e to the power plus I phi. Okay. So this is then for a single electron, this is what the Gn would look like. And now you could write these in terms of the x, y, and z components of that vector. Remember, what we considered was this electron which is pointing in some direction n. The spin is pointing in some direction n. And its wave components of the wave functions were the c and s. And so we wrote down the corresponding this matrix electron density, or if you call it the Gn. And this is what we ended up with. And this we could write as half. See, 1 plus cosine theta. Cosine theta is like the z component of n. Because if you remember, I think I had written it earlier, that the x, y, and z components are like cosine theta, and then sine theta, sine phi, and then sine theta, cosine phi. Those are the x, y, and z components. So this is 1 plus nz, this is 1 minus nz. And this is sine theta e to the power minus I phi, which you see is like sine theta times cosine phi minus I sine phi. And sine theta cosine phi, that's the x component. Sine theta sine phi, that's the y component. And when you look here, it's the complex conjugate of that. So you get this. So this theta and phi then, when you go back to the x, y, and z components, would look something like that. So now you can see the basic point I was making, that if you had an electron pointing in some direction n, and you tried to write its electron density, this Gn matrix, it would look like 1 plus nz, 1 minus nz, nx minusiny, nx plusiny. So what if you had n electrons? Well, you just add all these up. So the 1 would become the capital N. That's the total number of electrons. And this nz, that represents, of course, the z component of the spin. So when you have n of them, it will all add up to give you the total z component of the spins of all these electrons. That's the Sc. Similarly, here when you add it all up, you'll get the total x component of all the electrons. Hundreds of them, whatever it is. Similarly, Sy, Sx plus Sy, n minus Sc. Same thing. And of course, this half is out there in front. as I had mentioned. So this is how you could see why the Gn looks like this. So when you calculate Gn from from the NEGF method, for example, this is how you'd interpret it. That is, you'd look at what's on the diagonal, that would tell you n plus Sc and n minus Sc. You look off diagonal, you'll get Sx and Sy. Okay. Now, as I mentioned earlier, that this particular form, it's convenient to write it in terms of what are called these Pauli spin matrices. And of course, what we did in the last module, if you remember, that also had a similar form to it when we wrote the gamma. That is, the gamma looked like alpha plus beta over 2, I believe. And then it was like 1 plus Pz, 1 minus Pz, Px minus Ipy, and then Px plus Ipy. So it kind of had that same structure to it. And the way you can write it, and this is, let me write down these matrices, and then I'll try to explain how you do this. And I'm just introducing notation in the sense that the basic result is right here. All I'm going to show is that in terms of a set of matrices called the Pauli spin matrices, you can write them in a certain convenient, compact way. And so these matrices are the following. So identity matrix we all know, that's this 1, 0, 0, 1. That's the identity matrix. Now, the Pauli spin matrices, the sigma x, there's a sigma x which is written as 0, 1, 1, 0. Then there's a sigma y which is 0, minus I, plus I, and 0. And then there's a sigma z which is 1, 0, 0, minus 1. And in general, any 2 by 2 complex matrix can be written as some linear combination of these. So you could always write it as, something times this plus something times that, something times that plus something times that. Okay? So these are these Pauli spin matrices. And what I claim is that this Gn that we have written here, you could write it like this. Half of, like we had before, Ni plus sigma dot S. Okay. So this sigma is this Pauli spin matrices. And it's not obvious that that and this are the same thing. That's what I'll try to show in the next minute. That's what we'll do right now. So the way you see that is by saying that, well, let's write this out. You got a half, and then you have n times I. So that looks like n times 1, 0, 0, 1. Now, what's sigma dot S? Well, that's where, of course, it's a little misleading because this S is a number, a vector with 3 components. This sigma is kind of a matrix vector, right? There's a sigma x, sigma y, and sigma z. So when you say sigma dot S, it's like sigma x, Sx, plus sigma y, Sy, sigma z, Sz. So sigma x is 0, 1, 1, 0 times Sx, plus sigma y is 0 minus yi plus I 0 times Sy, plus sigma z is 1, 0, 0 minus 1 times Sc. So you got these 4 matrices that you need to add up. And what I claim is, and this just takes a little algebra to see it, is that when you add these 4 matrices, you'll basically get back what I had there. So just look at the 1, 1 point. So this point. So it's like n times 1. That's 0, doesn't matter. That's 0, it doesn't matter. And this is Sc. So you get n plus Sc. Go to the next one. This is 0, doesn't matter. That's Sx. This is minus Isy. This is 0. So you get Sx minus Isy. Similarly, you can check out the other ones. So the basic point is, something like this can be written compactly in this form in terms of these Pauli spin matrices. Okay? This set that you have seen here. And similarly, the gamma that we had obtained earlier, like in the last module, that could also be written in a compact form. See, it could be written as alpha plus beta over 2 times I plus sigma dot p. Because once again, if you write it out, I plus sigma x px plus sigma y py plus sigma z pz, you'll get back this full form. So you could view, in a way, this is like a shorthand notation for that one. You could view it that way. But once you get used to these matrices, it's actually very convenient when dealing with all kinds of problems. And that is because these matrices have some very interesting properties. It goes something like this. That if you take, for example, if you take any of these matrices and just square it, so like sigma x squared, the answer is it will be I. It will basically be the identity matrix. And you can show that. Or you could say multiply two of them, sigma x, sigma y. And the answer is it will be like sigma z, actually with the I in front. And if you reverse the order, like may write it as sigma y, sigma x, you'll still get the same thing but with a negative sign. That is, as long as x and y are in the right clockwise order, x, y, z, it will be I times that. If it's y, x, then you get a minus. So it has these very interesting properties that once you get used to it, it makes it very convenient to get all kinds of results. So for example, one of the things I said, that how when you have spin polarizer and an analyzer, that is, if you had these two contacts, one's this way and the other is in some other direction, then the amount of current or electrons that will go through is this cosine square half theta. Now, that's something I stated earlier, but in order to see how it would come out of this NEGF method when you multiply these matrices, that's where again it's convenient to show it if you are familiar with some of these identities. And that's what I guess in one of the homework problems, which we'll be discussing in the tutorial, I'll go through some of these identities that are very useful when dealing with the Pauli spin matrices.